All right, good morning, guys. Welcome to the second day of the conference. We'll be starting with Alex from Netris, who is going to talk about the network architecture when building AI clouds. Give it up for Alex.
Hi everyone, thanks for coming. I hope you're doing well. No hangover from yesterday's night. I'm Alex Saroyan. I'm the CEO and co-founder of Netris. At Netris, we work with various vendors, including NVIDIA, and we happen to be NVIDIA's network automation partner for their Ethernet-based GPU cluster networks. So on this presentation, I'll share about GPU cloud networking based on our experience and some insights from our work with NVIDIA and their customers. So I have a few goals on this talk. So I want to tell you about how can you and others build and operate networks that are similar to those that AWS, GCP, Azure, these guys build and operate, but you can build and operate this kind of networks on your own hardware suitable for your scale. I'll tell about specifics of GPU networking, how it is still networking, but there are some things that are a little bit different in GPU world. And number 3, I'll try to keep the sales pitch to bare minimum. So we're going to talk about networking and cloud, and let's first define what is cloud. And let's not forget that cloud is, in the first place, for servicing applications. So cloud exists to provide managed services for workloads, to make VMs work, to provide storage. AI training is another workload that cloud is servicing for. All these cloud providers, they build some kind of abstraction layer that makes, that highly automates cloud and makes it accessible to all the users. But when we look under the hood of the cloud, we're going to find all the same hardware. This hardware is available for pretty much everyone, right? It's all the same servers, same storage, same networking. But 10 years ago, 12 years ago, when these cloud providers were starting, they had to reinvent everything. They had to develop their own compute virtualization layers, compute orchestration layers, storage, networking. Back then, a lot of technologies that exist today, a lot of open source and commercial products that exist today were not there 10, 12 years ago when cloud providers were starting. And today, we know that, CloudStack is there, right? There are other products that exist, open source products, commercial products that we love and products that have been acquired by some other companies. But the point is that there are options, and today if you are building a cloud, you don't need to reinvent everything from the scratch. So we can say the same about compute, about storage. Networking is a little bit different because in the field of networking, we don't have lots of different options. It is hard to build cloud using Microsoft Excel and a bunch of bash scripts. So the networking automation and abstraction challenge for cloud providers was such a big challenge that we founded a company. So we founded a company to address this challenge. And I promise that I will keep the sales pitch to the bare minimum, and I'm gonna stay to my promise. But I will share from our journey. We've learned a lot, we've done a lot, and it's interesting, and I think you're here to learn from our journey. So, networking always evolved, driven by workload needs. Remember, even mobile networks, they started to evolve only after iPhone came out, right? People started consuming new kinds of applications that required more bandwidth, and that's why mobile networks evolved. Cloud created VPC, the concept of VPC. Remember, before cloud, there was no VPC. And now, today, VPC is about 10 years old, and VPC appeared to be very useful construct. Cloud would not exist without VPC. Similarly, world-scale web applications, they necessitated creation of CDNs, such as Cloudflare and others. And, just like it always been in the history of networking, next evolution in the networking will be, again, dictated by a new kinds of workload. And this is a workload that most people are sick and tired of hearing about, which is AI training. Now, this chip here, this is a very popular GPU, H100 by NVIDIA. Lots of known models are being trained on these GPUs. And thing is that every AI workload in the world wants to make it to the inference. See these AI workloads that are being created by AI, data scientists, AI companies. They basically crunch enormous amounts of data sets, so bunch of numbers, bunch of images, and they train and train and train. And sometimes this training takes months. Sometimes training takes months, and results are not great. And then they tweak some parameters and they retrain the model. So it's a continuous and long model with the goal to make it to the inference, to start making money, obviously, of the trained model. AI training is the most expensive workload by far. This by order of magnitude. This is like 1,000 times more power and computational cycles hungry workload. Now, imagine this, even motherboard required to be reinvented. See, on this screen you see kind of a typical motherboard that's used in all this HGX, mostly DGX servers. So not exactly this one, but this is like example motherboard. And on the left side you can see the area that is similar to traditional motherboard. You can see slots for 2 CPUs, slots for RAM, and on the right-hand side, this part is created basically to service GPU workloads. So these slots, these are 8 GPU slots. We can see that 2 GPUs are installed, but typically all 8 GPUs are installed here. It appears that even PCI bus isn't fast enough for GPU to GPU communication. So NVIDIA built this protocol, this technology called NVLink, which makes GPUs to talk to other GPUs, avoiding PCI bus, but using NVLink bus, which is more performant than PCI bus. And the latest versions of NVLink, they can deliver up to 900 gigabits per second of communication, non-blocking between every GPU on the motherboard. So this allows for 8 GPUs to talk to each other. And why would GPUs talk to each other? That's because the amount of the size of data set that you can train your AI model is limited to total memory, GPU memory on the server or on the network. We'll talk about that soon. So this H100 GPUs, they have 80 gigabytes of built-in RAM. And on this board, you basically connect these RAMs together. And And this is how much data set you can feed into this training process. But data sets of today, we are talking petabytes. We're not talking gigabytes, right? So how do you do that? Now, so data scientists, they have these methods of parallelizing the training process. So when they run parallel training on larger number of GPUs, you probably have heard, models being trained on 20,000, 16,000, 100,000. We've heard this, largest AI cluster in the world is 100,000 GPUs. Now, here's the deal. Every AI training cares about training time because this training takes months. And training is always a function of number of GPUs, data set size, and model complexity. Now, model complexity that is measured in billion parameters always grows, right? Every time data scientists create new model, it is more complex than prior version of the model. And data set continuously grows because they always want to train on larger amount of data to basically make smarter models. So the only way to keep the training time to reasonable is to increase number of GPUs. And here's a detail. GPUs can talk 400 gigabits per second to other GPUs. This is what modern GPUs are capable of. And parallelism methods require that every GPU talks to every other GPU at that 400 gigabits per second speed. If one GPU's network is degraded, let's say, to 25% of total capacity, so let's say instead of being able to push 400 gigabits per second, one GPU out of 100,000 GPUs is limited to 100, the entire network performance will be limited to that smallest performance on the network. So if network gets in the way of only one GPU, the entire training time is affected. This is very different compared to web scale applications, right? With web applications, if one server is not performing well, that's probably not a big deal. Most users will not even notice that. But here, one server not performing well affects the entire business, basically. So how industry addresses these issues? So first of all, these large GPU clusters, they are connected over a network, multiple networks. And one network showed here at the top is what we call north-south network. And these GPU servers, they also have CPUs on the board. This is where your operating system runs. This is where kernel runs. This is where applications that make GPUs work run. And this part of the server still needs a network. This is where data scientists connect to servers. This is where storage connects to the network. And these north-south networks are typically 200 gigabits per second. Now, how does this compare to your traditional data center network? It is still leaf-spine network, but your typical high-performance data center network would be 25 gigabits per second to every NIC. And this is 200 gigabits per second to every NIC. Now, this north-south network being very performant by itself is not enough to carry all the data required for the training purpose itself. Because see what happens. Every GPU can push 400 gigabits per second, and you have 8 GPUs on every server. That makes 3.2 terabits of data being pushed. And if you try to push 3.2 terabits into over 200 gigabit links, you're trying to put 3.2 terabits into 400 gigabits pipe. That is 8x degradation, which will make this basic network of 2 GPU servers, this network of 16 GPUs, will perform like it's 2 GPUs. So to alleviate this problem, industry is using another network, the east-west network, And for the East-West network, they are adding NICs. NVIDIA calls those super NICs. So these NICs are aligned with the GPUs. Every NIC is basically internally connected to each GPU using technology called GPU Direct. Now, GPU Direct is an interesting technology. See, the idea here is that to expand memories, right? We want to connect memory pages of the GPUs together over the entire cluster. And if we do this the traditional way, the network traffic would have to go through PCIe bus and the CPU, and that would hog CPUs, and we would not achieve our goals. Now with CPU Direct, NIC has direct connection to the GPU's memory. So basically, network is able to read and write into memory. With that said, East-West network that is usually 400 gigabits per second per NIC. It is non-blocking full duplex, 400 gigabits per second. And by using technologies like RDMA, which is native in InfiniBand, RDMA allows to connect memory blocks of different GPUs together. Now, as I said, network always evolves driven by workloads, and when this new workload, AI training, required connecting memories of a bunch of chips together, we came to technology called RDMA. You all know probably what DMA is, direct memory access, and RDMA is remote direct memory access. So RDMA was there in InfiniBand networks forever, with a smaller throughput, of course, but what happened, industry increased the throughput of InfiniBand to 400 gigabits per second per link, and by using RDMA in this East-West networks, we connect memories and workloads that are running on these GPU servers. When they perform memory operation, they see this collective memory as a single, combined memory on the server. This allows for fastest communication between GPU memories, which has to be 400 gigabits per second. Now this has to be lossless, and InfiniBand delivers that lossless networks. And this has to be non-blocking because we are talking every endpoint sending and receiving 400 gigabits per second all the time, non-stop. If network blocks this communication at any time, the training process will crash, and data scientists will need to restart the training. They can potentially lose weeks or months of training, or they would need to go back to the latest checkpoint. And checkpoint is GPU-intensive function, so they cannot checkpoint like every hour. They typically checkpoint every few days or so. Now, technology was evolving, and users wanted to use Ethernet network for East-West, and just because you have to have these multiple networks, you have to have North-South network for storage connectivity for accessing the cluster, which is always Ethernet. And it is hard for operators to manage networks of two different technologies. So now recent developments in Ethernet world made Ethernet networks also possible for East-West switch fabric. NVIDIA has this Ethernet technology called Spectrum X. Broadcom has their own version of it. So this Ethernet technology, see, unlike InfiniBand, where InfiniBand is lossless technology, Ethernet is lossy technology. So Ethernet can lose packets, and this is kind of normal in Ethernet world. But it's not normal when you are replicating memories. Now, in Ethernet world, we are using technology called Rocky V2, which is basically RDMA over converged Ethernet. This is like simulation of InfiniBand network over Ethernet network. So with Ethernet East-West fabrics, this is basically regular Ethernet network using EVPN and BGP on the underlay. It is connected a little bit differently in a rail optimized design, what we call, which is non-blocking design. So you have a lot more switches and a lot more links to deliver non-blocking connectivity. Now, even in single tenant networking, when amount of links and amount of GPUs and amount of switches is this high, it is complex to manage this kind of networks. But for a single tenant network, this is usually one-time configuration, one-time complex configuration, and then you train models. Now, but this talk is for cloud providers, right? So how do you separate these GPUs into tenants? Because when you invest in these very expensive GPUs, you don't want to use all these GPUs for just one training. You want to rent GPUs out to your external customers, maybe even internal customers, but you want to carve out groups of GPUs into tenants and give to different groups to train models. Now, this requires isolation on the switch side. That is coming for two reasons. One is, basically security reason. You don't want two tenants traffics to kind of access to each other. That's security part. You don't want noisy neighbors. You cannot afford noisy neighbors because of bandwidth and latency requirements that we have in AI training. And also the way that parallelism works, the technology that runs behind parallelism and using that NVIDIA tool called Nickel, NCCL, it wants network on the east-west fabric to be fully isolated on a switch level. Now, when you're building this kind of network for building a GPU cloud, you're gonna face two challenges. How to dynamically and automatically carve out these isolations on the switch side. Tenant comes in, tenant goes away. You all know this, right? It's the same challenge in regular networks. And challenge number two is gonna be how do I provide connection from the internet to this isolated tenant so data scientists can access clusters, can connect storage, can upload data sets and stuff. Now, this hyperscale providers, they invested years in building their VPC solutions deep into their switch networks everywhere on their infrastructure. And, VPC was a abstraction created by cloud providers, and VPC abstraction is still very much applicable to this problem. But it took these hyperscalers years of time to invest to build all these automation tools, which is challenging. But 10 years ago, that was the only way. So I'm gonna keep the sales pitch to the bare minimum. So, bless you. So what we do at Netris, we've built same methods of abstraction, of isolation for everyone else to enable every other cloud provider with these powerful abstractions. Now, I will not go through every feature of Netris. There's Q&A. You can ask questions during Q&A. We have a booth here. You're welcome to come to our booth and ask your questions. Just to summarize this, NVIDIA been innovating the space with the hardware. They created, new kinds of switching silicon, new kinds of NICs. They created this GPU direct technology, all that. But one area where we had the opportunity with partnering with NVIDIA was automation of these kind of networks. So I've budgeted some time for Q&A. So feel free to, I'm coming from technical background. So feel free to ask technical questions, business questions, what it takes to build a cloud and all that.
Any questions? I do.
So if you want to run your private cloud offering as a tenant-based system like Amazon or Azure, where does your system play if you're running CloudStack in terms of the overall layer of the services?
Yeah, that's a great question. So, in fact, we have another presentation at 2:30 today in the other room that is completely about CloudStack. VPC abstraction is applicable to any cloud that you are building, and we've in collaboration with ShapeBlue, we're building this integration with CloudStack, which allows kind of expanding VPC multi-tenancy functionality of CloudStack into the rest of the fabric, connecting CloudStack virtualized networks to non-CloudStack networks, because oftentimes you have your GPU part of the offering, bare metal GPU part of offering, you have your CloudStack offering, maybe you have something else, right? So you need to connect these things together. And there will be this detailed description of this at 2:30.
Thank you.
All right, thank you. Any other questions?
Any feedback about this?
Can you give oh, you're recording, okay. I know you committed to not giving a sales pitch. I'm interested in at least an elevator pitch, though. From a soft-gate perspective, we went to the side pretty quick. Can you go over what the soft-gate appliance or offering from Netris handles in terms of the specific stack that you're talking about?
Mm-hmm. Yeah, thank you. Good question. So part of the cloud offering is not just switch fabric can just isolate things, right? Provide kind of high performance connectivity between endpoints, but there are things that as a cloud provider you have to provide and switches cannot deliver. Things like internet gateways, cloud gateways, elastic load balancers. In traditional networking, these functions would be provided by routers or firewalls, right? But when we think about cloud, traditional routers, firewalls would not fit, and would not fit because of scalability challenges. When you design a cloud, you're talking millions of VPCs potentially, so you want a design that scales to that scale. And if we look under the hood of of hyperscalers, AWS, for example, they don't use hardware firewalls or load balancers for these cloud networking functions. They are using servers and proprietary built software that runs in parallel, scales horizontally, and is VPC aware. So SoftGate is basically that. It's a Linux-based software. We use open source offerings when open source products, when possible. We improve these open source products. Sometimes we add to open source products. And we put together all these different components into SoftGate. And SoftGate is your software gateway that provides cloud networking functions. SoftGate integrates with the switch fabric that's managed by Netris, meaning that VXLANs travel all the way into SoftGate. So SoftGate can terminate 16 million different endpoints. And it provides these functions: internet gateway, NAT gateway, and elastic load balancers.
All right, I think we have one more minute for any other questions, so happy to take if there's any. Okay, in that case, thank you, Alex.
Thank you so much.